Well, thank you very much for the kind introduction and for the invitation to speak at this nice meeting. So I want to thank Dražen, Samayuki, Annie, and Nils for organizing this wonderful event in such a lovely place. I don't know whose idea it was to bring us here, but it's definitely a great idea. So today I'll talk about several bridges between topology and algebra. So usual way that these fields are related. My background is more in topology, or rather quantum topology. And usually the way these fields interact with each other is that one starts with some algebraic structure of quantum algebra that will involve quantum groups in our discussion, or perhaps even more relevant, vertex algebra. And then from this, one produces invariants of three manifolds and knots. In other words, algebra serves as a fuel for constructing topological invariants of knots and three manifolds. And today, part of the surprise will be that there will be a feedback loop, namely a relation in the opposite direction, where quantum invariants of three manifolds and constructions in quantum topology provide something back in algebra, and in particular motivate why certain vertex algebras should exist. But first, let me start with less surprising direction of this connection, where we go from algebra to topology. And I'll try to make a general table also to explain where some of the things that will be discussed today sit in the big picture. And I'll organize it in the form of a table where there will be three columns, 1, 2, and 3. And first column will be about topology. So here we'll talk about invariants of three manifolds today. So by topology, I mean low-dimensional topology of dimension 3. In particular, one can try to organize the structure in terms of topological quantum field theory, TFT. And then columns 2 and 3 will be about algebraic structure. And here in the middle column, I'll discuss relation to quantum groups or corresponding underlying quantum group structure. And it's also convenient to think about categories, which in relation to quantum groups could be a representation categories of the corresponding quantum group. Category also goes in here. And last column will be about vertex algebra. For the rest of the stock, I'll abbreviate as VOA. So the first and perhaps most well-known example of quantum group invariant is a set of invariants of Witten, Reshetikhin, and Puraev. So I'll write it as WRT, invariants of three manifolds. The corresponding algebraic structure is based on a category, which in this case is a Verlinde category for some Lie group G and integer k, usually called the level. So it does have many realizations, this category. In particular, it has something to do with quantum group. So we can consider quantum group for any root system. Today, I'll just mostly focus on Cartan type A1. Namely, we'll do it for SL2. And important point here is that Q is a root of unity, namely kth root of unity, where k is this integer, the level. And we can consider corresponding category of modules of this quantum group, but focus on a semi-simple version of this category, namely consider semi-simplification. And that's the important part, which will be generalized in the next row of the table. But at least here, if we talk about semi-simple categories, of which Berlin categories is an example, the corresponding VOA is fairly well understood. It's a rational VOA, namely corresponding WCW model or Kac-Moody of the type G at level K, where again G is Lie group and K is integer level. So this is the first row of the table. So next we'll continue with generalizations of this construction, trying to model each of the columns, namely relation between topology, quantum groups and categories, and vertex algebras. So I'll proceed to slightly more esoteric instance in this table. So the next sort of line will be the following. Suppose you're interested in more exotic sort of invariants. And some of them involve, say, Rochlin invariants, or invariants introduced by Akutsu, Deguchi, and Otsky, often abbreviated as ADO invariants. So similar invariants were also studied by Murakami, Jun Murakami, Christian Blanchet, here, Costantino, here, Poitras-Morand, and various other people. So that's going to be, there is a whole collection of closely related invariants. For this general review, I'm not going to make a sharp distinction, but I'll try to emphasize some of the qualitative points. So in this column, where we talk about quantum group, it's also representation theory of quantum group at the root of unity. So Q is still root of unity, but which quantum group we take now becomes quite subtle and in some sense reflects the whole variety of different closely related invariants that we can take here. It could be a so-called restricted quantum group, or small quantum group, or of completion, so usually denoted phi of SL2, or unrolled quantum group. And there are many, many other variants. So important point is that, again, here, Q is also root of unity. If I am to emphasize big picture kind of important things, so Q is again root of unity. But what's important about all these different categories is that they are not semi-simple, and they have slightly different structure, which again reflects in slightly different variants of these invariants. And another new aspect comes up, which is not going to be terribly important for most of what I'll say, at least. I mean, it is important, but I want to emphasize it later, is that here we start having automorphism. So in the previous context, automorphism of this category is nothing, so it's trivial. And correspondingly, the class of VOAs, this WZW models labeled by the same G and level K, also don't have non-trivial automorphisms. But here, in this setting, depending on, again, which version you consider, but most typically, automorphism group is going to be PSL2. Sometimes Z2s are important. I'm not going to make a big fuss about it. And also, if you generalize to higher rank or general Cartan type, there will be interesting interplay between a group and Langland's dual group. But again, today everything will be for SL2, so you may safely ignore it. So there are, again, closely related algebras, vertex algebras, which relate to these categories and realize them as tensor categories or categories of their representations. And perhaps one of the most familiar or famous such algebra is 1, k triplet VOA, but what's important is that it's not the usual VOA, it's logarithmic. And this reflects the fact that here we don't have semi-simplicity in this whole row. So this entire row is about something which is non-semi-simple or logarithmic, but still happens at the root of it. Okay? And this whole talk today is really going to be about the next line. So that's why I'm trying to put this map so you know roughly where it feeds. So we'll talk about the so-called GPPV invariants. So as sometimes they're referred to these days. So this is based on joint work we did a while ago with Luca, Pavel Putrov, and Kumran Vafa. And this associate to knots and three manifolds some Q-series invariants. I'm going to, so usually they're denoted Z hat, and I'll decode many of these notations later on. So they take values in integer power series of Q and correspond to quantum groups at generic Q. So here, if I were to put quantum group on a board, I would probably put UQ of, again, SL2. Everything today is for SL2. So what I can say is that Q is generic. And usually assumed to be inside the unit disk. But, I'm not going to talk much about it today, but in construction of this invariance, certain ingredients of this quantum group at generic Q enter. In particular, Verma modules, infinite dimensional Verma modules with generic complex weights play a role. Finite dimensional modules, finite dimensional modules. But these ingredients enter at the level of constructing invariants of three manifolds and surfaces. But in the language of extended TQFT, it's actually hard to say what should be the right category. So it's tempting to say, well, let's just write a representation category of this quantum group. But we have to define what this thing is, namely what we include. It's clear that we should include finite dimensional modules and Verma modules, but it's not clear how much else should be included. Probably something, but this is not terribly well understood. In other words, this object does not exist fully as an extended TQFT in the sense that one can talk about all levels of three manifolds, dimension 3, 2, and category would be dimension 1. So therefore, this I'll focus today on this side of this table. This box is half filled, half empty, depending how you look at it. And this box is completely empty because, in other words, here I can write a big question mark because it's not clear what vertex algebra should correspond to this situation. Morally, it should be WZW model at complex level, whatever that means. And people have tried in old days to construct such WZW models at random complex level. But as you can see, there are certain things that one wants to meet in such construction, which are fairly specific. For example, one wants to have Verma modules, or one knows what Grothendieck group of this category is, and it has a nice structure, so I'll write Grothendieck group here. Hopefully it's not too dense. It's basically weight lattice of the original group times the dual lattice divided by the Weil group, which is very reminiscent of something toroidal or double affine. And again, all these old-fashioned constructions of WZW at complex level don't usually achieve that. So therefore, this to me is a big question mark. So this is one of the problems which are problems for vertex algebras. And I have no idea, again, how to fill this box, but this is a hard problem. That's not something I'm going to suggest today in the end of the lecture. So this is still trying to go from algebra to topology in this direction. And even though invariants that I'll focus on deal with such objects and do require connections to VOAs, these VOAs are not known. So this is a big. What is in this setting? So this yeah, it's easier to say what Grothendieck group should be, but of course it doesn't tell us immediately about what the generators or elements of this are in the category. So I can try to make a attempt. Maybe it will be easier after the lecture using Verma model. But again, this is like I say, Grothendieck group is a projection of a category. So strictly speaking, we don't. So that's a question. Yeah. So for oh yes, yeah. Sorry. Yeah. So the question was, I am emphasized that there is not fully extended structure, and there is something which exists at level 3 and 2, meaning 3-dimensional manifolds, 2-dimensional surfaces, and not 1-dimensional categories, where this was already like a kind of a little question mark. And David is asking, what's the vector space for surfaces? So for torus, so it's natural that category we associate with circle, and Grothendieck group of that, or tensor with some field perhaps, could be vector space for a torus. So basically, vector space for a torus in this DQFT will be C of this. And that one is pretty sure about. So this will come up even in some things I'll say today. And there is something known about hygiene. So this is reasonably well under control, but not the category. And the question, again, from this line broadly defined, is to upgrade it to suitable category, and better yet to VOA. In other words, find WZW model at complex K, which has, I don't know what that. Complex number enters here because Q is generic inside the unit disk, and everything. So yeah, so that's a good question. Therefore, when one feeds this construction of quantum algebra and produces some topological invariance, what usually happens? One takes some, say, 3-manifold and makes all these representation theoretic choices. For example, picks choice of Lie algebra, which for me today will be SL2. Pick the choice of level. In old days, this would be choice of K, which is integer, and a negative integer. And based on this data, according to this arrow, one would produce some 3-manifold invariant or invariant of knots. And for instance, WRT invariant would be a good example. It would be invariant of a 3-manifold, and it would depend on the level K, and that's it. So to answer your question, where complexity enters, or in a sense of complex numbers, now K is replaced by Q. And they're still related in this way, but Q is generic now. So therefore, given the same starting point, namely 3-manifold, choice of Lie algebra for today of Cartan type A1, and Q, which is generic complex number inside the unit disk. So that's the complex number. The outcome will be of a similar type. So it will be some class of invariance. Let's call it, again, that hat B. but they'll depend not on K, but K is now replaced by complex level. So they'll depend on K. And question is, what are these objects? So today I'll tell you a little bit about this object, just enough so we are not in a vacuum. And then surprise, or surprising part, that's part of the title, is that now by looking at this object, we'll see the arrow going the other direction. So that's going to be the point. Does it make sense? Are there any other questions? All right, so my next goal then is to tell you a little bit on how to construct these fellows before we try to study their properties. And we'll start with the following theorem due to Licorice, Wallace, and Kirby. So this is, if you're not a topologist, the next few minutes will be a crash course on low-dimensional topology or topology of three manifolds, just to give you an idea what a three-manifold looks like. And it says that this theorem says that every and now connected, oriented, closed three-manifold M3 arises as integral surgery on some link, or people usually start with knots, which are links with only one component. I'll denote it by K sitting inside a three. Well, this is a useful sentence, but what does it really mean? How can we understand that? That's, I'll try to decode it in a second. First, I want to clarify that this does not mean one-to-one or uniqueness. For instance, there are many, in fact, infinitely many knots and links which give rise to same three manifolds upon surgery operations. So surgery will be explained in a second. But for instance, if you start with three sphere and do so-called -1 surgery on trefoil knot, you obtain the same manifold as doing +1 surgery on another simple knot. So this 3-1 and 4-1 are notations for knots and links that topologists are frequently using. So 3-1 is something I can draw. It's not which like this. 4-1 is a little tricky. I guess it will look more like this. Anyway, I'm not sure I'm drawing it right. This one has 3 crossings, the other has 4 crossings. This is why 3 and 4. And the point here is that there are many ways, in fact, infinitely many, to construct same manifold from this theorem. So it's highly non-unique, but there are very few equivalence relations that relate different constructions. So to make it a little bit more tangible, let's look at the following case of knots and links. So simple example of a knot K is just a knotted circle. So that's something easy to understand and visualize. And doing integral surgery means decorating this with an integer number. For example, -17 is a good integer number. It doesn't have to be positive. And what this means is we take three sphere where we think this object is embedded. We excavate tubular neighborhood of this knot or link, and we glue it back, deforming a twist. So the neighborhood of this knot or link has a toroidal boundary, and the mapping class group of this toroidal boundary is SL2Z, so then we basically focus on elements in SL2Z labeled by this integer here, such that we reglue it back with this integer. So that's where integers are coming from. They're telling us how to reglue things. So suppose you have now, what is a link? So this is an example of a knot called unknot. Unknot. And these are other knots, for example, trefoil knot. And this is usually called figure 8 knot. But what's an example of a link? So the theorem requires to do integral surgeries in general on link. And these are basically knots which are linked together. So for instance, this would be a link called Hopf link. I take two circles, link them in a non-trivial way. And here I have two components, so I can decorate each one by an integer. So let me say that this is -17, and this would be, I don't know, +8, for instance. That's a three-manifold. So that's what a three-manifold topologist looks like. Well, now I'm starting to compose this with non-trivial knottedness diagrams which look like this. And again, if you haven't seen this before, you probably don't like it now. It's too topological. So let me keep it in the realm of combinatorics for a second and say that, well, look, this diagram can be represented in a much simpler way by saying that if you have just unknotted circles, I replace each one by a vertex. Whenever they're linked, I'll draw an edge and represent the same data by -17 vertex connected to +8 vertex by an edge. And this looks much nicer. It's a combinatorial data of a graph. And now you can think of a statement of this theorem by drawing any graphs you want. For instance, let me give you an example of a graph. Something like this. So I have lots of vertices. They have to be decorated by integers because we're doing surgeries. So A1, A2, A3, A4, A5, A6, A7, A8, A9. Yay, we got 10 vertices. A10. And this is a three-manifold topology. Okay, so basically all three manifolds to them look kind of like this. So I promised you a crash course on three-manifold topology. So using this rule of converting links into graphs, you're allowed to draw any graph you like. It could be a graph of our friends on social network or some other graph, like linking diagram of something. There are, of course, infinitely many graphs that we can imagine, just like fish in the sea or stars in the sky. It does look kind of like constellation. Comparison to stars in the sky is not random. But the point is we have graphs plus this integer decoration. And this is already a huge universe of three manifolds. So that's what three manifolds look like. And to give you names, continuing with this crash course, these graphs are called Fleming graphs. So each one, according to this theorem, defines a choice of three manifolds. And I promise this is the only blackboard where I subject you to too much of topology. So now I'll try to come back slowly to quantum invariance and then to vertical. Okay? So that's it as far as topology goes. We're done. I promise you there'll be no more topological data. But if there are any questions, I'll be happy to answer. And I promise to repeat the question. Yes, so that's a very good question. So like I said, it's not very non-unique. So natural question, which was asked by Rob Kirby, or is exactly the question you're asking, namely, what are the relations? So good news is that there are very few relations. It's just like when we define knots using some planar diagrams, there are 3 Rademeister moves. So in this context, there are basically 5 Kirby moves. So good news is that there are only 5 of them, even though the universe of possibilities is huge. So this is actually one of these instances where your space of possible configurations is humongous, but number of moves is very finite. So this is actually perfect for machine learning. So that. So what are the examples of these moves? I wasn't planning to say anything about it, but since you asked, I'll just give one example. And again, 1 out of 5. Suppose we see a piece of a graph, and I'll do it using this graph notations, not using the knots only. Suppose you see a graph with a vertex decorated by some integer a. So all these ai's have to be integers. They represent these surgeries. So equivalence relation says that you can do operations, so-called blow up and blow down, by replacing this ai by ai either +1 or -1. Both signs are allowed. If you connect it to additional vertex, labeled accordingly by +1 or -1 as well. And you don't change the rest of the graph. That's an example of Kirby move, or in this context, more proper name would be Kirby-Neumann move. Okay, any? For us, this universe of graphs will be, and they may have loops and very interesting structure, will be enough for construction. Yes. So let me comment on this a bit later, because if there is something funny, then I probably won't be allowed to use language graph. So this works only if my individual components are unknotted and they're just linked like this. So they're either linked or not linked. Yeah. So if there is more non-trivial knottedness, in a sense, it's exploring either high linking numbers a la Milner or more topological self-knottedness, I should use this language. So this theorem still applies, but simplification in terms of graph will yeah, that's right. So given such a graph, let's introduce the following notion. So let me define a metric Q, which will has the size of number of vertices by number of vertices in this graph. This will be basically adjacency metric, and it will be equal to ai on the diagonal values if I is equal to j. It will put 1 every time I and j form an edge, and we'll put 0 otherwise. Then, assuming that B is a choice of element in the co-kernel of this metric Q, so we can assume the determinant is non-zero for simplicity, and then later, if we wish to generalize it to that case, when it vanishes, then we can make the following definition. So I can finally introduce what this invariants look like. So given such a graph, so M3 here is defined by the choice of graph. Again, the proper name is Fleming graph. Q will be generic, just like in the blackboards that I raised, or over there, it will be complex number inside the unit disk. This will be principal value multiple integral over big torus. So we'll introduce lots of complex variables xj, as many as vertices in a graph. For example, in this example, there will be a 10-fold integral to do. Then product over xj running in the set of vertices dxj over 2 pi I xj. We're basically taking the constant term for the residue of x to the 0 of the following expression. Product of xj minus 1 over xj to the power 2 minus degree of the vertex j. This is basically valency. So if you have a vertex which has some number of legs coming in or out, this is what we're going to call the degree. And we'll take a convolution of this with a big theta function defined by the quadratic form of all these x's and q's, where theta function, I'll write it down on the blackboard, but it is what you expect it to be. It is, I'll say, where this big theta function associated with the quadratic form and characteristic B is defined as a huge sum over integer vectors in Q times the lattice whose size is number of vertices. B is the offset in the sum. I'll write it and then I'll send the blackboard further up so you can see it. Then any theta function is organized such that it's q to some quadratic power. So here it's going to be quadratic form based on q, and then product over I, xi to the ni. So I'm going to erase this presentation of three manifolds, but this is outcome of this machinery of using quantum groups at generic Q, which produce invariants of three manifolds as functions of three manifolds and Q. So far, this looks like topology, or as I promised, I'm moving toward quantum topology. So there is no vertex algebra in sight. So, but again, surprises will come in a minute. So far, this looks very much like what quantum topologists want to calculate. They start with a choice of three manifolds given by such graph. They feed in this quantum group or whatever else. Q is generic. The output is, of course, depends on choice of Q and depends on choice of manifold. And this is done. So it's very concrete, very explicit. It's written here as a huge integral. This is not what we ask our students to do in a calculus class. For instance, here it would be integral of multiplicity given by number of vertices, but it's easily done using residues. And by playing with it, you can quickly see that it's actually a very finite compact sum. So it's infinite sum, but it's nicely organized and then easy. So this is something which is very, very computable. So that's exactly the question we're going to ask next. Yes, we are going to ask this question. No, it's not going to be modular form. Right. So we talked a little bit about topology. So I gave an example of how this invariants are invariants of graphs. And if you trust me, there is a generalization to any three manifold where you substitute this rational function by something that depends on knots and links. But now, next question we're going to ask is, indeed, how does it depend on choice of Q? So from the functional point of view, so I assure you it's extremely easy to calculate. And if we had more time, or if you ask me later, I'll be happy to show various simple Mathematica codes which implement this for lots of graphs. So it's fun to play with. So it's extremely computable. So that's the punchline of this part of the talk. But next question is indeed, what is it as a function of Q? So what we addressed the dependence on M3. So what is the dependence on is this clear? Any other questions? Yeah, so that's going to be part of this theorem, indeed. So I'll list in this theorem several properties of this object. And yeah, so since you asked, maybe one important point is that, so I'll say that, for example, for M3, and then we have several bullet points, one of which will be that it's invariant under Kirby moves. In other words, it's a well-defined invariant. Otherwise, we wouldn't be talking about something. But there was another question. Yeah, so you can have loops, multiple edges, and also zero eigenvalues of this metric Q. All these questions are actually connected. So let me relegate it as advanced topic and discuss in the end if we have time. But yeah, so there is a generalization. It's actually the same thing, that it basically forces us to go back to the original language of knots and links rather than graphs. That's why I have either option of presenting simplified version, which is, again, big enough universe for us, or we can keep in mind that there is something much bigger that covers everything and that belongs to that big. All right, so then, indeed, so the first theorem in this entire business was basically the statement about some properties of this object that we construct in this way. So it has several properties. So it's invariant under Kirby moves. So that much is already anticipated. But now, as a function of Q, we have to understand what are the basic properties. So first, is it even a formal series in Q or function? What kind of series it is? So it's easy to see that at least for Plum, and here the word Plum is important, it's convergent in Q inside the unit disk. So this is relatively easy exercise. You can do, for example, ratio test or other check and then see that. More importantly, it has this object has integer powers of Q and also integer coefficients. So in other words, it looks like, again, if we had more time, I would compute for you a couple of examples, even for this graph that we had on the board or some other graph, so we can see it with our eyes. We can experiment with Kirby moves. I chose to do Blackboard rather than computer, so it's not easy for me to do it now. But we would see that even from simple few experiments, we would see that it looks kind of like this, where coefficients C0, C1, C2, and so on are all integers. So this object lives in power series of Q with integer coefficients. Delta can be negative, so it can start with a negative power, but CIs can be negative, yeah. In general, CIs can be negative. There are not in simple examples, but there is a priori no reason for them to be positive, because this integrality, so this is a remark, this equality is a remark, it's not part of the theorem, it's where this comes from. This is meant to be sum over I and j minus 1 to the I, q to the j, dimension of doubly graded homology group associated to a three-manifold. And that's, in some sense, that's why the fact that it has integer coefficients is not a surprise. This object was engineered in such a way that it's counting something, that it's a virtual character of some vector space. And a priori, these vector spaces are just some three-manifold invariants. And for topologists, that's the primary interest. But for us, primary interest is dependence on Q. And last bullet point in this theorem would be the following statement that, which in some sense was also part of the original motivation. B has been defined, I just erased it. It was here, it was in a quaternion of Q element. It's a choice of element, namely for any B, everything I say. No, that's, there is a simple formula in terms of doing this integral basically over from scratch. If you ask what kind of invariant of a three-manifold this delta is, it's actually a very precious for topologists question. The answer we don't know, and suspicion is it may be related, well, it is certainly related to very delicate cobordism invariant. So in Hilbert-Fluor homology, there are so-called D invariants or correction terms. So modulo 1, this delta is related to that. So that already shows it's actually quite non-trivial. No, it's yes, up to this delta. Yes, integer powers. Yeah, that's why I put this delta aside. Yeah, apologize. That's what I meant. So delta B is a rational number, and integer powers indeed refers to. Yeah. So in fact, you already see where I'm heading with. So if you think about characters of VOAs, well, that has the same structure, right? But anyway, let's go slowly. So, like I say, these coefficients, integer coefficients, are counting something, and well, natural question is how fast can they grow? So Tomoyuki asks, can be they positive or negative? So both signs are in principle allowed. There is no reason for them to be positive, because again, morally it comes from something that should be counting things with signs. So a priori, I have no reason for them to be all positive. But what can we say about their rate of growth? So suppose I have a series which is 1 plus q squared plus and so on. I know how fast coefficients are growing. So in fact, if I multiply this by q to the half, this can be easily written. I mean, this whole series is just geometric series, so I know what we're talking about. And this can be viewed as counting of energy levels of, say, harmonic oscillator from quantum mechanical system. So, and the fact that here we get rational function with one denominator is basically responsible for the fact that we're counting one single boson in physics language. So in quantum mechanics, the bottom line is that dimension of Hilbert space whose degrees are bounded by some n always grows as n to some power. And this power basically tells us how many bosonic degrees of freedom or how many denominators we have, or factors in the denominator. Well, suppose I have something more advanced. Say, let me start with an eta function. I'll write it as eta of q, but it's of course the same as eta of tau, 1 over 24. We usually know this as infinite product. And from 1 to infinity, 1 minus q to the n. And suppose I look at 1 over eta. So now I'll have infinitely many denominators. So there'll be 1 minus q, then 1 minus q squared, and so on. So q to the minus 1 over 24. So if I expand it as a series in Q, I mean, it's clearly a series in Q, how fast would coefficients grow? Okay. So I can write it in exactly that form. namely say that this is q to some delta, C0 plus C1q plus dot, dot, dot. And a theorem is that they grow, so Cn grow exponentially, but with a very precise rate. Exponential of 2 pi, and then there is square root of n. And usually we call coefficient of that square root of n 1 over 6, and then C effective, which is in VOA or CFT literature is called effective central torque. In this case of eta function, it's going to be equal to 1. So C effective is equal to 1 here for this example. But in general, in any unitary VOA, you can prove that this is exactly the growth of coefficients of its characters, which is much faster than this power law. So roughly speaking, this tells you a difference between what physicists would call 0 plus 1 dimensional quantum mechanics and 1 plus 1 dimensional quantum field theory. So in quantum field theory, you have a lot more, and that's this a lot more. Basically, infinitely many. So here comes the first surprise. So I told you in the first part of the talk how to compute this invariance associated with generic Q. And now we're asking how do they look as functions of Q? They could have looked in any way they wanted. A priori, they come from three manifolds. They come from this part, the quantum topology. So they could have had any behavior in Q. They could be just monomial in Q. They could have been 0, in fact, or some constant, or they could have had any sort of growth of coefficients. But surprisingly, they have exactly this growth of coefficients. So that's the first prize. And that's part of the title for this talk, or part of the punchline. So this motivates the following conjecture, which is sometimes called 3D modularity. Although in retrospect, this name may not be ideal because it's not really about modularity, as we'll see in a second. But this is how a question arose. People were asking basically exactly this question: what are these objects? So we know they're converging inside the unit disk. We know roughly how they look like. Natural question is they kind of look like modular something. Are they modular? So that's where it came from. In retrospect, it seems that it has more to do with vertex algebras than modularity. So it should be called like 3D VOA because it comes from three manifolds and leads to vertex algebra type objects. And conjecture basically says that if it looks like a character, it should be a character. So therefore, if we think about this as a character in vertex algebra for a given choice or for any three manifold, then this object is a character of logarithmic VOA. Logarithmic because it's easy to see from where it comes from that it cannot be fully modular. And it should have some messed up modular properties. And this is not uncommon in logarithmic vertex algebras. Moreover, trying to take it seriously and starting with simple manifolds given by, say, graph which consists of a single point labeled by something, you can identify what VOA is behind this, and you quickly see that it actually lives in the world of logarithmic vertex algebra. Yes, it's a super vertex. Yeah. So when I say VOA, I tacitly assume that it's super. And this VOA depends, obviously, on the choice of three manifold, but does not depend on choice of this label B, which I completely suppressed in today's discussion. The point is that if you have different B's for the same three manifold, they will give you characters of the same algebra, just different characters. So that's what I'm saying. B was in our context defined as a quaternal of Q, but more generally, this takes values in H1 of a three manifold with integer coefficient. The slope VOA depends on M3, but yeah. Well, there are different characters for different modules of the same thing. So these are modules labeled by B. Modules labeled by B of the same VOA. So what I'm trying to say, this clause, parentheses, belong to log VOA part. So VOA does not change. It only changes as you change manifold. And different B's pick out different modules or different characters. So of course, this is hard to check. But what you can check, in particular, if this statement is true, it implies, if this conjecture is true, it implies something very, very verifiable. It means that coefficients Cn grow exactly as written on the other board for some constant C effective, namely this very peculiar exponential of square root growth. And now this becomes extremely concrete. So I told you how for pretty much any graph that looks like fish in the sea or star in the sky, how to compute this invariant. There are so many of them. So there are infinitely many opportunities for this conjecture to fail, or at least this part, but it hasn't failed so far. And the question is why. So therefore, I promised you some questions or problems to work on. So questions include the following obvious ones. So prove or disprove this growth. So either prove or disprove. Let me call this formula star, this rate of growth that we know from unitary VOAs. By the way, even from, so another question which I'm not going to put here is that even in the context of logarithmic VOAs, they are non-unitary. So usual proof that coefficients grow this way uses modularity and unitarity. So here we know that these objects are not unitary nor modular. So therefore, even in log VOA context, I don't know such a theorem which would say that the coefficients always have to have this growth. So technically, we actually don't have that. So there is just within VOA something for us to do. So prove or disprove this for surgeries on links. So I'm mostly focused on the simple types of links, but in fact, we can repeat this exercise for general ones, and we're always going to find the same growth. So maybe start with proving this for some simple families, like for torus knots and links, and generalize. That would be a good strategy. Another question has been asked in a slightly related context. Namely, what is delta in terms of three manifolds? I don't know the answer. It's a very subtle invariant. Here, if you're thinking about this bridge to VOA, question is, what is this C effective? What is this number? So we compute this. There is an obvious number, which is basic characteristic of vertex algebra, typically. It's defined as central charge minus the minimal conformal weight. So what is this from three manifold topology? So in other words, what combination of three manifold invariants is this number that controls the rate of growth? I have no clue. Both of these questions, of course, can be answered by trying to explore this behavior in some families. And thinking about this, most ambitious form of the question would be to actually construct what it really suggests, and this is something that should be true, motivated by, again, physics and other things, is that not only characters should be associated to a given free manifold, but actual vertex algebra. So therefore, the most ambitious part here would be to construct a family of logarithmic vertex algebras, log VOAs, labeled by these graphs and invariant under Kirby mode. In other words, what we're seeing here in these questions, first few questions, is just a shadow of a richer structure. And again, claim is that there are deeper reasons that suggest that the answer should be there. It's just hard to get to it. But in principle, this is all you need to know to start thinking about it. That there are graphs, there are certain relations between graphs, so we should have VOAs for each equivalence class of the graph. So these are progressively harder. Okay, I'm running out of time, so if organizers allow me 2 more minutes, I'll give you one more surprise. I don't know if it's legal. Okay. Well, thank you for being so kind. So I just wanted to conclude with one more thing, which came out very recently, and is actually useful to start thinking about this question. So the way I phrased it here, it looks like how to explore the growth is clear because, again, I try to emphasize that everything is super easy to compute. So it's very easy to play. So numerically, with relation to characters, we have a lot of points to start exploring. But question in terms of constructing an actual log VOA seems much harder. Like, where do we start? I mean, there could be lots of things with the same character after all. So recently there has been something that surprisingly sheds light on this point and suggests where to go in a way that probably many of you know better than I do. And just like in the past, I was lucky to learn from some of you many elements of this beautiful subject. So for instance, I'm grateful to Tamayuki, to Thomas, to Anton Milish for teaching me many of these things. So hopefully what I'm going to tell next will also resonate with you and you'll come back to me and say, well, now it's clear how to answer even this last most challenging point. And this piece of structure that I want to share with you is the following surprise, that a priori, I told you how to compute this object for many 3 manifolds, and what comes out of this calculation is some Q-series, the structure that I very briefly told you about, but it wasn't clear how to write it in a closed form. So in particular, if you want to explore, unless we're dealing with super simple manifolds in general, it wasn't clear at all. It's just some Q-series, and you can write thousands of terms, but if I give you thousands of coefficients, how do you know what it looks like? I mean, the best you can do is start checking that behavior of coefficients satisfies the formula we expect of characters, but what else can we say? It turns out that in this business, actually coming from physics, so this last bit, I will share a little bit of physics, but again, only as an output, that behind every such problem, there is a so-called BPS quiver. So this is connection to quivers. Because these integer coefficients are supposed to be counting something. I mentioned this earlier, and they're supposed to be counting some structure associated with this quiver, usually called BPS state. And sometimes this quiver looks like this. So let me just give an example. So it could have, say, 3 nodes interconnecting. There could be some circular loop, say, in this form. And then you would associate, and let me make this maybe double edge. So then to this data, you also associate a tone metric, which is analogous to metric Q that I introduced before. It will be of size 3 by 3 because there are 3 vertices. Each time we have loop starting and ending on the same vertex, we'll put corresponding number on a diagonal. So here the numbers will be 0, 2, and 3. For 0, 2, and 3 loop, each time vertices are connected, we'll put number of edges or links that connect them. So here we'll have 1, 1, and 2. So such quiver is encoded in the metric T. And then, surprise is that all these complicated looking formulae turn out to be multisums over integers, di, which are non-negative. And number of such sums is equal to number of quivers, nodes in the quiver. So here it will be sum over 3 non-negative integers. Universal denominator, which is product of Pachheimer symbols associated with these di's. And then Q to basically D, T, D, quadratic form based on this metric. Kind of similar to what we saw before, but again, in a very, very different context. Plus some linear terms linear in D, in Di. So this subject was developing kind of by itself in the past 5, 10 years. And keywords here are BPS and quivers, and this was self-contained universe. But those of you who are old enough or read papers from 80s quickly recognize here that forms of this type were also particular forms of how, in old days, people wrote characters of vertex algebra. These are called Fermionic form. So in VOA, this form has a name and has a meaning. It has a meaning because the number of rows and columns in this metric tells you about integrable deformation of vertex algebra, which retains its quantum group structure. So relation between quantum groups and vertex algebras that we were discussing in the very beginning, going back to 80s when the quantum groups were invented, is actually exactly about this fermionic form. That's how the connection or Kazhdan-Lusztig correspondence was actually born. So by rewriting the characters of VOAs in this specific form, with this metric C, one actually learns something about our metric. This metric C is a close cousin of our metric. And again, the point is that it has its own name in that subject called fermionic form of VOA character. And something that modern developments, well, modern, I mean 10 past years or 15 past years, didn't realize, and that was completely independent development based on quiver. In that subject, this form is called quiver form. And using this quiver forms, we now have a good way of rewriting in each instance this Q-series invariance of 3 manifolds in the form of fermionic character. So this is quite recent. It's basically a few months old. This very connection, and as a result, it provides basically now a new foot in the door to understand what are the vertex algebras behind some of these 3 manifolds, namely maybe helping with this question, because now this is a closed form. It's still a multi-sum, but it's a closed form expression. So I apologize for running over time, and we'll be happy to answer your questions.
So thank you for the wonderful talk. Is there any question? Yeah?
No, but that was actually motivation for this entire development, to be honest, at least from quantum topology point of view, because this doubly graded homology is meant to be analog of Khovanov homology for 3 manifolds. So that's for topologists and quantum topologists. This is probably the main motivation. It's extremely hard to compute. So that's why I really can't say much about it. I mean, I know what it looks like for a couple of simple examples, but that's not good enough. That's much worse than computational power here, where one can compute these objects now for surgeries on any links or nodes up to 10 crossings. So this is much under control. But what I want to say, maybe in the context of this connection to VOA, is that if you really figure out what VOAs and modules these are characters of, we basically help topologists, because we basically give them the vector space whose graded character is this theory they're looking at. I don't know. Like I say, I think this is new, and many of these things, especially the fact that it turns out to be character of something logarithmic, is surprising to me in many ways. I don't think it's being explored enough to answer this. Yeah, so regarding the two gradings, maybe, I don't know if this will help. One grading is obvious. It's conformal vector grading by L naught. So that's the same as always. The other grading is a little mysterious. What can be rational? Well, only in the same way as it is for usual rational unitary vertex algebra. So up to, I mean, there is overall power of Q, which is rational. Everything else is integer. So raising and lowering within, say, Virasoro or other parts of the algebra by integer or integer grade.
Any other questions?
Oh, yes. Right. So cases where it's known are, you're going to laugh. So it's very little is known. So that's why I'm a little bit embarrassed. But they are. So they definitely fit within today's discussion in the sense of labeling manifolds by graphs. So we don't need anything much fancier. The list of examples is not very long. So, so first, if you have one vertex labeled by some integer p, then this is non-logarithmic, non-log VOA, and that's the only case I know. And characters are extremely simple. This is basically q to some number divided by eta. So we all can guess what this is. More interesting cases start when you have these graphs. And what matters is how many high valency nodes you have. So if you have only one trivalent node, then here you find 1, p singlet log VOA. If you have trefoil knot, that's one of the knots I was drawing earlier, so that what you find is 1, p, or actually more general porous knot, I should say, triplet log VOA. They differ because in this case you have non-trivial automorphisms and characters are functions. So here character is just function of q, and here character is a function of q and one of the x variables we had before. And I don't know what Anton is going to talk about tomorrow. His title may suggest that he may give us some more examples, but in the paper with Catherine Brinkman and Carl Malberg, they explored examples of this type, for instance, where you have two trivalent nodes. And this becomes, at least in this case, they know what function of q is. It's high adept Mach modular form. High adept Mach modular. I don't think one should take this Mach modularity too seriously, even high adepts, because it's easy to see that once we go to more general knots and links, we quickly run out of this modularity. But this illustrates that basically examples that are known are very, very simple graphs with small valency. In this case, it's also hard to say because that's related to your other question. So in most of the simple examples, these coefficients are all positive. And it looks like just this other grading, which was -1 to the I, is not even activated. So we don't, we don't see it. Well, you saw my talk last week at Simon's where I showed some 10 crossing knot, and then there were minus signs, but you have to really go to very complicated knots and links to see minus signs. So I know they do show up. Otherwise, I would state a conjecture that coefficients are always positive. In fact, for graph manifolds, maybe one should add this as a proof or disproof that coefficients are always positive for graph manifolds. So far, I have no counterexample. But for more complicated knots and so again, I don't know. That's the subtle information about this other grading to which I have no access. And if there is any insight from VOA perspective, that's
Thank you.
Yeah, so I could say a lot of physics gibberish. For instance, there is so-called 3D correspondence, which assigns to three-manifold supersymmetric three-dimensional theory. That's why it's called 3D. Three-manifold gives you 3D supersymmetric theory. And so-called half-index or Q-cohomology of that 3D supersymmetric theory is exactly what we're talking about. But again, that's good to know so that we have motivation that all of this is as another kind of board. But mathematically, this of course, useless. So that's why I hide it from you.